First thing I want to do is a systems of equation. I was disappointed, let's just say. Shouldn't take too long. Okay. So this is something I thought was not too difficult, but I guess we're learning. So thing is, then it was an obstacle because a few questions were based on it. So let's go ahead and so let's have a system of equations. Let's just say 2x plus 3y plus 4z equals 5. And then second one, x minus y equals z equals x, why not? And then x, no, let's leave x out of this one. So 0 equals plus y plus z. All right. Okay, we have this question. Transform this system equation in matrix form. Like this, x equals d, where x equals, yeah, that's maybe some other. So a v for variables, where v equals c, and is a vector of terms. So let's do this. It's practice day, so please do that. And if you don't know, ask and learn. Yeah. Um, yeah. So these are the three equations. So please write them this way: AV equals D, or and yeah. Thank you. So is that going to give us some solution? Yes. Even iPhones can try it at home. So here the trick is to be systematic and avoid sign mistakes. So let's just say 30 seconds and then I'll show you how to do it. Okay, so let's do it. So step one, put variable on left hand side. And the constant terms. So this is already good. And then, so I have x here, so 0, and x minus x. So of course, x minus x is 0, so I get this. And then minus y minus z. And then, so make sure that they are in the right order. If you somehow would like to make it even more systematic, you can add zeros for coefficients if they don't appear, but it's just trust ourselves that we're not going to make a mistake. So okay, so I have x, z, and then so what multiplies x is 2. What multiplies y is 3, and then z is 4, and then this is equal to 5, right? Then what multiplies x? There's no x here, so it's 0. Y is minus 1. Then z is 0, and this is equal to 0. And then 0 minus 1 equals to or build the matrices. All right, so I'm confident I'm going to ask you something like this at the final because I was a bit disappointed by the performance. So just to continue on this trend, so let's do the reverse. Now consider the system change stuff a bit. So -1, 0, 2, 0, 0, 0. Why not? Not saying it's a good system or anything. Or for 0. Then it's 1, 2, 3. So right system has 3 equations. So this is there's even fewer steps. I think I did it this way in the, it was last year's midterm, maybe. I started with this form and I said write it as an equation. Okay, so let's do it. So all you have to do is multiply this with this, and you should be good. So, multiply question matrix with the variables. Vector. Right. So here we get those two. So minus x plus, so 0 times y plus 2z. And this is 0, 0, 0. And this is 4, 4, so 4x plus 4y. And that's good. So this is equal to, of course, still equal to this. So if this vector is equal to this vector, then each element of each vector are equal with each other. So zero equals, oh Jesus, what did I do there? You were you like waiting for me to realize my with power? Okay, no. Yes, but still, I don't want this to be associated with my name anyways. So let's add something wrong there. So this is going to be x. Yeah, maybe it's unsolvable anyways, but no, it looks like it's, yeah, it looks like it should work. But who knows? We have to check to be sure. And then all right. Okay, so this is how you should do it. So yeah, we can go on and compute. Well, why not? Why don't we continue? Well, no, that was the midterm. So I'm not going to, spend. Maybe I'll ask you stuff with it, but mostly I have so much to cover for the final, anyways. So that's about it. Okay, so let's go with the final. No, that was one of the classes. Um, and don't worry, I haven't started writing the exam, so I'm not going to fall accidentally on it. Okay. So as I was telling, so what happened last time is the midterm was a bit easy, and then I overcorrected. So don't be traumatized if you think it's too difficult. Anyways, yeah. So I would say, yeah, it's not a long question, so we can do the sets thing. Okay, so what I think I'm going to do is copy the questions and then question. For the following statements, replace the question mark with by equal if the left and right sides are the same, or not equal if they are not. If they are equal, show it using Venn diagrams. If they are not, show it using a counterexample. So think about it. Are they equal? Are they not equal? So it's all about associativity, but as you're looking, so associativity, normally you have a single operation. So you see something like addition is associative or multiplication is associative. So you have one operation. So this looks like it should work because intersection is one operation, but this seems fishy to me. So I don't know if I should do it. Should I leave you like 1 or 2 minutes to think of ways in which you can show or disprove them, and then we can. And by the way, that's going to be a nice way of showing how I would like you to answer in the final. So something like this. It's funny, why do I see only one person there and 6 there? Oh, yeah. Okay. Yeah?
Venn diagrams is easy.
Mhm.
But like, if you think about like this numerical accepted example, and not like think of it for the gift. What are some tips to that? Like, just use like the set of numbers that.
Okay, so how you would do if we are in a math class, a real math class, how you show this? Well, if you want to show that two things are the same, what you have to show is pick any element of this set and show that it is in this set, and then pick any element in this set and show that it is in this set. So, but I've never, even myself, I've never like really worked out this kind of proof, but that's the way you do it. And it's, of course, at the end, it's going to just be like Venn diagrams, just formalizing it, right? But yeah, so we shouldn't worry. So Venn diagrams are nice because they are visual, and, but yeah, but proof by drawing is never convincing.
But the thing is, my diagrams are used in mathematical context.
Mhm. So they're there to prove by showing like a circle is within some other circle. So there are like tricks, like people will show something like, oh yeah, if I take this and I remove this part and then I rearrange and then there's some cube that square that appears and then oh, but it's just that you didn't. Your drawing was kind of that well.
Economics, how is it used? Like,
Oh, sets.
expression of equations or?
Yeah, sets. I don't know. I think it's just the foundation of math, so we start with it. But yeah, I can't say. Mhm.
I've seen it in probability, I guess, but like, it's related, but I don't know.
Yeah, economics is about the world, so math is about the world.
Yeah,
So
yeah.
these two have some common theme, but yeah, but yeah, real close applications, I'm not aware. Okay, so let's do the first one. Yeah, so I think for then people at home, I'm going to change to. Okay, so hey, let's have three circles. So this is A. Yeah, then the same. Yeah, it's. Anyways, we know what the statement is. ABC. So of course, if at the exam you're not sure if they are the same or not, start with Venn diagrams. Then if you find out they are not the same, see that would like be kind of perfect. So I couldn't remove a lot of points. So if I'm telling you, please give me a counterexample, then yeah, that's what you should do for full points. But if you show me with the Venn diagrams that they're different, I'm still quite happy with it. Okay, so that's A inter B, right? A inter B inter C. So A inter B is this. So I should do this. This is like not there yet. And then yeah, no, let's just leave it this way. And then so that's A inter B. and then A inter B inter C. So the whole thing. Yeah, it's tedious to do it on the computer. It's just so easy to do it in the mobile. So while I'm doing this, think of a counterexample for the other one. So then that's this blue plus enter this one, so I get to the center. And then second one is I start with B enter C. And then A enter B enter C is exactly like this. But please draw it again. So just to be clear that you're going to think two different things, but yeah, you're going to get the same thing. So that's A. And then, so this is false. So can somebody think of a counterexample? Just think of some sets A, B, and C where it would be false. Not so easy to think of that actually, but once you have it, then it works. So obviously, I'm not going to expect you to find something super complicated. So just try some simple things, and you might find that it shows that they're different. Yeah, a set with of A, of B, and of C. And you show me that A inter B union C is different than A inter B union C.
Like 3, 4, 5, 6, 7.
Yeah, exactly. That's exactly what I want. So we try it and we see if whether it math is a lot of trial and error. All the time we know what we would like to show, but we're not too sure yet how to do it. So A equals counterexample. A equals 3 and 4, you said?
Yeah.
And then C equals what? 5, 6, 7. A good exercise just to try our luck, see what we get. So A inter B is 2, 3, right? 3. And then A inter B union C is 2, 3, 5, 6, 7. And then let's try the other. So now we start with B inter C, B union C. like this, and then start. So B and C equals 2, 3, 4, 5, 6, 7. And then A equals not a lot, right? 2, 3. Oh, gee, we're not lucky. Ah, okay, so let's try something different. So yeah, that's something though that's so in some classes I was going to, sometimes they ask prove something or don't disprove something. You have to have some luck to get something that works. So some other
But this is true, right? Three is not the same as
oh, okay, no, I was looking at this thing. Oh, it works.
yeah.
Oh, okay, I sorry, I thought it didn't work. I was looking at that and I thought, oh, how lucky are we? So yeah, so yeah, okay.
But I have a question. You could work with that diagram, right? And because of that diagram,
Yeah, exactly. It's just that now I said please do it this way, but so it's different from so if you're really unlucky and you find two things that are the same, so try some other example. All right, so that was one. And then okay, we're already starting getting into the weeds of things. Good. So now this is after the midterm. Okay. So just to be clear, so this means that uh, so is the way. Okay. Consider the functions f of xyz equals z3, g of xyz equals log y log z, and h of xyz equals 1 over x plus y plus z. So A, find the find right any of the two. So write the gradient for each of them, and then are these functions within S functionally independent at this point x y z equals 1 1. So this is something that we've seen very fast at the end of some class. So it might be be a bit in the past in your head. By the way, I'm guessing none of you have tried the midterm, the final. This, yeah. So of course it helps if you've tried it once. So do you remember what is the gradient? So yeah. Okay. Anyways, I'll tell you. So the gradient is the the partial derivative. So a vector, we write it horizontally of partial derivatives of each function with respect to each variable. Okay. Now let me write this down. So the partial of let you do it with, let's say 2 minutes, and then and by the way, we write it with the yeah. So until now, it's fairly okay. It's what are the harder questions? Yeah, 3B was or 3D. Oh no, 3C. 3C was intense. I'm never going to give something like that. So let's do it. All right. So we write it in parentheses, and we write. So I'm not going to be mad if you forget and you write it vertically, but at some point you need to. Yeah. No. Please do it horizontally. That's the way we do it for grading. So here we have, so the f dx is 0, the f dy is 0, and the f dz is 3z. Okay, that's for f, and then j. Yeah, no, it's horizontal. Yeah, it's a row vector. Yeah. Because then later on for the Jacobian we stack them on top of each other. It's just it's a convention. So. Okay, so the partial derivative here is 0 and 1 over y. And then 1 over z. This is so. Do you remember how we do that? Yeah. So if I have 1 over x plus y plus z, so it's like if I had. So I'd like to do it this way. It makes things really easy. So it's just -1 like this, so -2. So that's minus. X plus y, right? Yeah. And then so that's the outer function, and then the inner function using the chain rule where, well, I have dx dx is just 1. So, and then, so I would get the same for y and the same for z as well. All right, so we're good. Then B. Are these functionally independent at xyz equals 1, 1, 1? Because of course, functional independence is so contrary to our linear system. Here, it can, yeah, the gradient can be many different things. Yeah, that's a neat exam question. So for a linear system, does the gradient change with the value of the variables? And the answer is no. But in this case, it does. So, so somebody who doesn't talk all that much, how should I do that? Yeah. Okay. So I'll remind. So once you know, it's not so difficult. So we build step one. So we know if they are. We want to know if these vectors are functionally independent or not. So if they are independent, then a neat way to know it is compute their determinant and see if it's a non-zero. Or you could also put them in some just in some matrix and compute the row echelon form. That would work too. Yeah, in the book they say it's determinant, so let's go with determinant. So yeah, build the Jacobian matrix. So which is yeah, of a vector of gradient. So you're going to see what we mean by this. So we write it J equals 3 by 3 matrix. And then we have so that's why we write them in rows, because we want to stack them on top of each other. So here we get 0, 0, 2, and 1, 1, and then so that's a Jacobian vector, Jacobian matrix for any value of x, y, and z. But now, of course, yeah, it could be nice to just to check what we get in general. Yeah.
Because we've seen it class earlier for like you have a triangle,
Mm.
and you could multiply corner entries.
Yeah.
Like, would it work in this case, even though the zeros are above? Like, if I go like 3, that's great.
So we just have to know what we're doing. So it's plus minus plus. So it's plus this multiplied by this determinant, and this is 0 times this minus this times this. So it would be, so you have a plus, and then here it's a minus. So there's a minus in front, but that works. But let's do it step by step. So we okay. So so the question is, so evaluated at xyz equals 1 and 1. So that's 1. That's 1. 1/3 squared, so 1/9. 1/9. So yeah, there's no imagination there. It's just you have to know what I'm asking and do it like a mindless robot. And then, but yeah, now you can have some imagination as to the best way to do it. Well, actually, we don't have to do anything. We know that the row echelon form is so it's I just have to flip them right there. We know it's independent. But let's compute the final steps. Here, the determinant. Determinant of G is determinant of this matrix there. And then you may remember the good way to do it is to start with a row or a column with many zeros in it. So either this column or this row, for instance. So for instance, let's start with that one. So determinant equals. Yeah, what's neat about this exercise, it's a link between linear algebra and the derivatives. So it's like a bridge between the two chapters. So that's 0 plus 0 plus 3 times the determinant of, oh, so yes, so that would be minus 0. So you see what I did there? I used 0 times the determinant of this, but it's 0 times something, minus 0 times the determinant of these two, plus 3 times this determinant there. And so this is minus 1/9. And this is so minus disappears. Yeah, 1/3. And so the
Interestingly, if you just did the switch up at first in the last row, it's automatically going.
yeah,
So
and
then you don't stop there. Right? If there's no like rows of zeros.
yeah. So what we were talking about is a fast way to compute the determinant. So since here we have a bunch of zeros, so essentially I know already that I'm going to have 3 times this determinant, but here again I have a 0. So again, this is irrelevant. So there's only this part that's interesting. So essentially I could just multiply 3 times 1 times minus 1/9. But there is the additional thing that this is, yeah, the diagonal is this way. So I have to add a minus in front of it. But I could have, yeah. Yeah, exactly. So this way would have been positive. Yeah. Right. So another way of doing it, so it would have been to just realize that if I flip the rows, then the sign of the determinant changes. But it's so if it's the only thing we care about is it positive or but is it non-zero or is it 0? And here, so the determinant is non-zero. So we a function, sorry. Independent. Okay, so if I ask you is to do this, that's just the recipe. So you compute gradients, you put them, you stack them on top of each other, you get a Jacobian, and you compute the determinant of the Jacobian. It's always going to work, and that tells me whether they are functionally independent. I'm just curious if I, just for fun, if I don't evaluate them at some value. So if any, just what I would get. There's no profound meaning in this, so I would get of so get J equals, so that's this times this times this, and there's a minus sign. Yeah, so anyway, so this has to be non-zero for sure. Y has to be non-zero. And if Z is non-zero, okay, so yeah, I'm screwed if. Yeah, okay. That would be a neat exam question, but a bit hard. I don't want to scare you, but yeah. Question is, what would give indefinite Jacobian would be XYZ equals. Yeah. So it's okay. Anyways, that was not the question. So let's move on. Yeah. Okay, 3. So 3 now things pick up. So I'm going to be a bit less. I presented things differently than last time, so I'm not going to be as yeah, as intense as this. Okay, so consider the following functions. Are they continuous or not? Are they smooth? If so, see whether they are C0, C1, C infinity. No need to justify. So here, yeah, because justification would take just forever. The thing that, so really what you have to do is look at them and ask yourself, so am I going to get a gap in it or not? Or a gap in the derivatives or not? So is somebody know, do somebody know what we're doing, or are you all confused, or? Yeah, more or less. Okay. So let's see the first one. So here, do you think it's continuous or not? No. Here it's not continuous. Why? What's the problem? Yeah, here the problem is you cannot divide by 0. And I have specifically said the domain is X is real. So it means that we have a problem. If I said something like X is 2 and greater values than 2, then no problem. But so A is no, so it's not continuous. So we say it's yeah, discontinuous. So what do we think? Are we going to get a singularity at some point or not? No, because whatever the value of x, 1 plus x squared is always greater than 0. Yeah, and then here at the numerator again, it's not going to create any problem. So really the problem are two big issues is sometimes you divide by 0 or yeah, there could be other things going on, but really the kind of thing I can give you is please don't divide by 0 and otherwise give you functions that are defined by parts. And defined by parts, obviously they can, you have to check what happens at some specific number, which is 1 in this case. So B is actually C infinity. So yeah, so we can just compute a few derivatives. So one, it is continuous. So I can just it's y equal x dependent on 1 plus x. Oh, okay, yes. All right, so it looks very nice. Yeah, exactly. That was just intrusive. Okay. So first, second, yeah. These are our function integrals. I'm going to tell you why. Okay. So now let's compute a few derivatives. So the more derivatives I can compute, which are also continuous. So it means higher the C something. So the level of smoothness. So let's go ahead and compute F prime. Um, so this is X. So yeah. So do you remember how we do divisions? So this, of course, please learn this at the exam. I can give you like 1 minute to do it because if you just look at me doing it, it's not as useful as trying it yourselves, unless you're super sure that you know how to do it. Yeah. So but quotient is fine. Some two people are computing. If I see nobody working, then I'm just going to do it. But as long as I see some people doing it. Yeah, sure.
Like, so is it x squared minus 2x? Oh, like,
Possible. So let's try it. Okay, so it's derivative of the numerator, so that's 1 times the denominator minus the derivative of the denominator, which is 2x, times the numerator, which is x, and then both divided by the denominator squared. So that's 1. So I get minus 6 squared. Yeah, almost. Yeah. So it's that's the thing too. It's something that you know the steps more or less, but if I put you under pressure with only 2 hours, there's the mistakes are just 5. So and then it's even hard just on myself or the person who grades it just to check where did the mistake come from again. All right, and so is this continuous? Well, yes, because again, it's not defined by parts, and again, the denominator is never going to be negative. We can just 0, so we can just check real quick. So it's 1 minus 6 squared. Divided by the same thing, but oh, now he's thinking a bit longer. All right. Oh, that's pretty. Wow, I didn't think I would get that. Yeah, it's asymptote. So it's again, all you have to check is okay. The denominator is never 0, and what you have to imagine is that where are we going with this? Well, if you take the second derivative, you're going to have something to the 4 and to the 6 and to the 8. So it's never going to be 0. So we can safely say, yeah, I can just
that's exactly what we-
yeah, yes, okay. But so I'm not asking you to do that, but yeah, that's exactly the sort of thing you need to have in mind. So is then by induction can write any derivative is also going so it x over f of x is if all right. And yeah, so the very intense thing I did with the third one, I'm going to tell you, is that you have to go until the fourth derivative to find something different. So at 1, like the function is the same, the first derivative is the same, the second derivative is the same, the third derivative is the same, but the fourth derivative is different. So it's because So it was, yeah, I think it was C4. C3 smooth, yeah, because the first is different. But so that was plus it took me forever to figure out a way to come up with this. It's very not easy because you have to always you cannot start by taking derivative. You have to take integrals every step to make sure that the constant term you are adding is going to make sense down the road. So yeah. Anyway, so C, don't worry about it. C left. Exercise for the interested student last semester. Okay. Yeah, really, I got carried away.
But in terms of C, would it be, is it at least C?
Yeah, it's C derivative. Okay, 4. So 4 is important. Let's do that. Consider the function. Yeah, I can just write it. F of x equals to 4 divided by 12 minus x2 divided by 2 plus 2/3 x minus 1. So there is a very, very, very big chance that something like this comes up at the final. So sorry for giving you nightmares if you don't like it, but it's not that bad. So if find all the critical values of f. So what should I do? Yeah, so critical values is either or infection point. Okay, so yeah, so I've realized that I didn't tell everything that I had to tell for inflection points, and anyways, it's not. So what we care about is minimum and maximum. So I shouldn't have. So I think I'm going to. So the only thing you have to know is if the second derivative is 0, then it can be an. Okay, I'm going to show you actually. So consider f of x sine mode. Inflection. If we have, let's have a simple example. So f of x equals x. So at 0, of course. So first derivative is 2x. 3x2. 3x squared. And then the second derivative is 6x. So at 0, so the first derivative 0. So 0. So we might think, oh, maybe we have a maximum, maybe we have a minimum. So let's check the second derivative. Yeah. 0 is 0. So 0. Oh, so all we know for sure is we can't say minimum, maximum, or inflection point. So then if you get this, just say, I'm not sure. Why is that? Well, let me just show you y equals x squared. X cubed, sorry. So I get this. Okay, we have an inflection point. And how do we know we have an inflection point? Well, because the rate of change of the derivative goes from it's decreasing, 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 and then it starts increasing, increasing, increasing. So it's so the rate of change is always positive. So positive, 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 positive. So that's how you would check whether you have an inflection point or not. Is you check the third derivative, and if it's always positive, if it's positive at 0, then we know we have an inflection point. But what about this other possibility? Consider this. F of x equals x to the 4. Then again, we can have that first derivative at 0 is going to be 0. So it looks like we have a maximum or a minimum. Second derivative, we find 6x squared. Oh, yes, sorry. Yeah. X squared. So, what's the second derivative at 0? Well, it's 0. Should we conclude that we have an inflection point? No. Because let me grab this one. Here it turns out it's a minimum. So that's so really, I'm just want to say that if you are looking for a maximum or a minimum, check the sign of the second derivative. If it's 0, don't bother. Of course, I could go more in detail why it's why you find an inflection point or not. Here, basically, the what's happening is it's the second derivative is negative, 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 becoming positive, and then, but it doesn't continue to become more negative. It starts to increase the other way. So that it's a very strange function. Yes?
Yeah, we also we can apply the first and second derivative and determine from here whether it's something to be x squared is also it's a independent value of x less than 0 and the independent value of x squared that's always positive.
Yes, exactly. So the right test, so the test to know whether you have a minimum or a maximum is you you check on the left-hand side is the function decreasing, on the right-hand side is the function increasing. If that's the case, you know you have a minimum. So this trick at looking at derivatives, you have to be careful. You see, the problem is it's never easy to just say, oh, let me evaluate my function at say -1 or who knows what the number should be. So that's why we always check derivatives. So that what I'm going to check to tell you is check derivatives. If you find that the derivative is the second derivative is 0, then just say that's outside my pay grade. I don't want to deal with this. So I cannot say.
But if you combine it with the first derivative, the first derivative is negative.
Yes.
So taking the information from the first derivative and the second derivative, combine them, and then compound again.
Yes, yes, yeah, we can, but it's really not, it's too advanced for economics. Yeah. So, okay. Second is 0, yet not an inflection point. Yeah. Yet 0 is not an inflection point. But all right, so really that's just a digression. Yeah. Side note and inflection points. I'm going to put this in all right, so going back to what we're doing. Oh, is it already finished? Okay, so well, let's continue here next time again. Well, yeah, so anyways, I wouldn't have time to finish it. So. So to the exam, there were 6. But yeah, in the final, I'm going to see. So you have 2 hours. I'm going to do something that's that makes sense for 2 hours. No, but I should know better. Take care.